CLion, a cross-platform IDE for C and C++. Download now.
So things I'm not going to talk about under this heading is I'm not going to give you a kind of full history and here's a family tree. That's fun. It's been done. You can find it anywhere. That's the normal way of looking at this. And it is enjoyable, and I'm sure I will do something around that kind of talk concept in future. This is going to be slightly different in this sense. So it's a case of I have a kind of an interest in programming languages and their history. I don't know if it's a healthy interest. I like the idea that all interests should be intrinsically considered healthy until proven otherwise. So I'm going to go with that one. And I want to talk about some things that, some of which I've been aware of for a while, some of which have only really occurred to me the last couple of years that I've started noticing and made a proper effort to look at. So yeah, you can find me pretty much anywhere. My name's Kevlin Henney. I actually live in Bristol, for those of you watching online. We are in Bristol at the moment, so it's a 20-minute walk to my house, which is that way. And you can follow me online, because that's kind of like 20 milliseconds that way, and that way. But based on some of the things that people have said in various talks, I have to tell you that all the jokes are mine. I mean, they don't originate with me, but I chose them, I selected them. All the photographs, with one exception, are taken by me. All the code was written by me. So I am to blame for anything that is wrong, but I also take credit for anything that is right. The reason I say that is as a way of anticipatory apology. The past, present, future walked into a bar. It was a tense situation. I don't know whether to say it gets better or worse from here. So let's talk about something actually slightly different. So last year I read this book by Anthony Doerr, Cloud Cuckoo Land. A lovely book, with sort of shades of David Mitchell about it. It spans many periods of history. There's a chunk that takes place around the fall of Constantinople in the 15th century. There's a chunk that takes place in the 20th century, chunk that takes place in the 21st century, starting a few years back and then passing through what is now the present and a little bit into the future. And then there's a bit that takes place in the future. But I'm going to read, I want to pick on a bit where we are, the focus towards the end of the book, Idaho State Correctional Institution, and the period of time covered is 2021 to 2030. For reference, this book was published in 2021. There's some he cunningly managed to get in the edits a couple of very small references to wearing face masks in. If you know how long it takes a novel to get published, it's just like, yeah, that was really managed, just a couple of light touches, and make sure that everything happened pre 2020, with just a little bit happening around now. But what is interesting, so there's a number of points of view. There's 5 distinct points of view in this story. But we take the character that is in the Idaho State Correctional Institute is a character called Seymour. I think it might be, the fact that he's basically in prison might feel relevant on the next slide. He spends every hour he can inside the computer lab. He's learned Excel, AutoCAD, Java, C++, and Python. Taking comfort in the clear logic of code input and output, instruction and command. Honestly, that fades really quickly, as everybody in this room knows. But the thing that I thought was fascinating is here's a novelist, an acclaimed novelist, and he's just listed off Java, C++, and Python. And it turns out, and this is supposed to be indefinitely in the 2020s. It turns out this is a very safe bet. So we're going to hop around time a little bit. First of all, I'm going to take you back to 1977. This is John Backus. And 20 years prior to this, so this is his, he was given the Turing Award in 1977. 20 years prior to this, he was responsible for what some consider one of the greatest crimes in the whole of programming language history. Fortran. It's an interesting one because it also helped kind of kickstart the whole idea of programming languages. One of the most important things about Fortran is that it wasn't really designed. It was kind of thrown together to prove a point. He and his team spent about 3 years at IBM trying to prove the point. At the time, the received wisdom was that you cannot create a system of a language that is automatically translated, i.e. compiled language, whose output efficiency is comparable to that somebody skilled in assembler would be able to produce. Okay? This was basically, you can't do this. So what did he and his team do? They proved that you can. Right, first thing, this gives us two things that we know about Fortran. One, that's where a reputation for efficiency came from, because that's how it started. That's always been part of its message. The second thing is that is why, linguistically, from a syntactic point of view and other things, it is a complete disaster area. Because literally they were making it up as they were going along. There was no consideration given to that. Anyway, he regards it as an experiment. Now, we all know what happens to our temporary experiments. It's just like, you know, oh yeah, this is just a temporary workaround. 20 years later, you are still supporting it and people are cursing your name. He's moved on. You can tell in the title, this is actually the longest Turing Award title, title I know of. Can programming be liberated from the von Neumann style, a functional style in its algebra programs? First thing, in case anybody wants to correct me, that says 1978. It was published, the speech was published in 1978. But the speech was given in the award was given in 77. Now, here's a couple of interesting things. A few points to note. One is this is one of the, in terms of Turing Award speeches, there's a lot of notation in this talk. I won't say I've read every one of them, but I've gone through them. He's kind of throwing a whole load of he really is throwing functional algebra at you. It's just like, I would love to have been in the audience just to see the general reaction of just general practitioners rather than hardcore computer scientists. The second thing I want to draw your attention to is the word style. He talks about style. Why does he not talk about the word paradigms? That's how we would talk about it. And you go through all the paper. In fact, if you look through any of the computer science texts of the 1970s, they don't use the term. Why? Because that was 1978's Turing Award. This, if you've ever wondered why we use the term paradigm in software, it's Robert Floyd. After this, you see the gradual increase of the word paradigm, okay? So basically, yeah. For all of his brilliance, John Backus could not tell the future. And we're going to see that play out. Because the point is, he's saying after 20 years, surely we should have kind of done better than Fortran. I mean, that's what he says, literally, in the paper. Programming languages appear to be in trouble. I want to remind you, he said that in 1977. So let's pick those three languages again that were in Antti Doer's book. Python, C++, Java. And what we see here is a top 10. And this particular top 10 lists Delphi and Object Pascal. I think that's lovely to all those Object Pascal users out there who aren't using Delphi, but you are such a minority, it's a rounding error. So we're going to keep things simple. Now, this particular top 10 is the TIOBE index, okay? And that's the one for March, which is current, even though now is April. March headline, the dinosaurs strike back. Funnily enough, actually, when I did an equivalent talk a few months ago, when I looked at that, that's the annoying thing about doing a talk like this, is you have to bloody update it. But Fortran was in the top 10. But it's just outside. But there were a couple of surprising entries. One is that Ada has made a proper vengeful return. But let me just show you what the top 5 looked like 5 years ago. September 2020. Okay, September 2020, C, Java, Python, C++, C#. September 2021, C, Python, Java, C++. Okay, 2022, 2023, it's 2024, and here we are now. Basically, this is the top 5. And each year we just kind of, churn out new permutations. Now, there is another thing here that's worth observing, is that sometimes people think in terms of rankings as being relatively linear. As humans, we are biased towards seeing the world in a number of different ways. We see things like Gaussian distributions in certain characteristics. For example, well, that's why we call it normal, because it is. But we also expect certain things to be linear or flat. It turns out that in this ranking, that's definitely not the case. It's a skewed distribution. It's not quite a power law, I did check, but it's a skewed distribution. Wildly skewed. I mean, of the 100 languages surveyed, 73%, so basically 3/4 are in the top 10. It's like, that is how skewed it is. And the top 5, that's 3/5. Anthony Doerr is safe until 2040. So here's an interesting thought about this. Let me give you another perspective on this. So first of all, the languages, there is a huge question of dominance in terms of the ones that are hugely dominant. That does not, let's be absolutely clear, that does not mean that there is no value in creating new languages. It just means when you, and it is not a measure of success unless your intended success is to dominate the market. If you create a DSL for 5 people and you have 5 happy people, yeah, that is a successful language, okay? If you intended to take over the world with your language, I refer you to IBM and PL1, which was so named in the 1960s, about 1965, PL1, because it was pretty much decided to be the last programming language. Anyone using PL1 here? Okay. Oh, no, using currently. No, yeah, okay, there we go. We had one there, that was a used, okay? But that's the point, is that one did not work. In fact, most attempts to create the final language generally fail. But let me focus on something else here. What do the languages in white have in common? They're all created before the year 2000. These are the ones that were created since 2000. And when I say created, there's obviously there's a couple of things I have to do when I go through looking at that, because what we regard, so for example, these days we have foundations and open source bases for languages, and that qualifies as something slightly different to how a language would have been developed and released, say, in the 60s or 70s. But reasonably, we can say in terms of initial implementations or initial official releases or whatever, it works like this. Okay, so that's that. Let's go and have a look at the top 20. See, Fortran, just outside the top 10 there, just knocked down a bit. Scratch, yeah, it is popular. It's popular. There's a lot of things here. Now, the problem with, this is the problem all the surveys have, in one way or another, they do kind of mess a few things up. For example, assembly language, that is not a language. That is a language class or a language type. You know, otherwise we've got 2 things: high-level languages and assembly language. No, so I'm going to knock that one out. So let's do that same thing. That's everything since 2000. That's in the top 20. And here are all the ones from before 2000. Okay, so you can see, if you look at the TIAB index, it kind of drifts over time. Now, some people are highly critical of the TIAB. In fact, most people are critical of each index that exists. There's a whole load of indexes and rankings and so on. They're all done via different criteria. I'm not here to try and favor one over the other. If you want to try and get a really good look at them, Connor Hoekstra's site, plrank.com, that's worth looking at. I want to get a feel for the shape of this. So let's go and look at another one, Red Monk. Very similar kind of drifts over time. The point here is that things do not change suddenly and overnight. Even if you're in a particular bubble, that's the thing, you've got to watch out for your bubbles. Because sometimes you're in a bubble and you go, oh my goodness, everybody's doing this. Oh, you mean there's people still using whatever language? And that, yes, there are, because that's actually most of what goes on in the world. So let's look at the Red Monk rankings. The point here is that it highlights the fact that change always comes later than we think it should. These are all old languages. They've got specific rankings in terms of, they choose GitHub, and they focus on rankings on Stack Overflow in terms of questions. Again, there are, of course, that's a self-selecting group. There's a lot of languages that never make a major footprint on GitHub because that's simply not the culture of the language. You don't find people doing that there. It's just not where those developers hang out. Similarly, Stack Overflow requires a particular demographic. So there is a huge bias in those. We like to think that those are flat and open. They are not. There is a self-selecting group. But let's have a look at their top 20. JavaScript seems to have a more credible position here. I'd say that feels a little more right. But there are other surprises here that I feel are slightly off. One thing, again, I see this in a lot of surveys. A lot of people put shell. Shell is not a fucking language. It's a language class, people. If you mean bash, you say bash, especially when you've got PowerShell in there. That's shell programming. So we got that. Okay, let's have a look at this one. So here's everything since 2000, and here's everything before. If we go and look at the IEEE Spectrum survey, that one's always interesting, and they actually look at different industry sectors as well. You can play around with their ranking. But that whole point about this being a highly skewed distribution, beautifully illustrated on their most recent survey from last year. It's just like, yeah. It's kind of like, it's kind of like, if Python is 1, then next one down is, only a half, yeah? And it just drops away to fractions from that. So you get a kind of feeling for how much more dominant the languages that are dominant are in the top 5, top 10, etc. really are. So this is what they've got. They've got the same shell problem, so let's fix that. And again, here's everything since 2000, here's everything prior to that. Now, at this point, we can kind of borrow from Bjarne's observation. There are only 2 kinds of languages, the ones people complain about and the ones nobody uses. Every time, whenever I have kind of done, in the past, I used to be a columnist for a number of magazines at various times, and I did a column for Application Development Advisor, 1998, I think it was, and it was about programming languages. I love going back and looking at some of my old articles to demonstrate sometimes how stunningly right I was, and also how amazingly wrong I could be. Now, I don't remember the details of what I looked into the future for, but I made a couple of observations about certain languages, pure object-oriented languages specifically, and I got a couple of people messaging me saying, "You're wrong, this language is better." Whoa, hang on. I'm not making a quality judgment, I'm making a quantity judgment. I'm not sitting there going, because these are the top 5, they're the best. I'm saying, these are the top 5, they are the most popular, or these are the top 10, they are the most popular. I think some of them suck. Everything is a bit sucky at some level, but there is a point here that this is a quantity judgment. So let's put all those languages together in alphabetical order. There's 30 of them, okay? And I've got rid of non-Turing complete languages, so HTML and CSS sometimes gets listed. I've left those out, and so we've got an interesting kind of view there. So that's one ordering. Here's a different ordering. This is by when they were created. 1950s, 1970s, well, something clearly happened in the 1960s. Did no languages happen then? Actually, there was a lot happened in the 60s and the 70s. Nothing much has happened since then. And I will justify that. I'm not saying nothing has happened. Nothing much is a very different phrasing. A lot happened in the 60s. All the languages pretty much that come after that were written by people who understood languages. I make that qualification because R and MATLAB are in this list. And those were definitely developed by people who had no idea about programming languages. But they all have a different character. There are ideas that they've started taking on, things like block structure and so on. But, just for a bit of fun, because I kind of thought there's a huge, great bump in the 1990s there. And, the 1990s gave us some really good stuff. But there's also sometimes, well, basically this is the millennial bump. Let's actually look at it from the point of view of Western social generations. That's much more fun. Okay? There's little Gen Alphas. Oh, Swift just gets in by some definitions of Gen Alpha. Gen Z, becoming dominant, but millennial, boom, that's it, And there's Gen X and there's the baby boomer languages. Now, what is interesting about this, I'm a Gen Xer, and what is interesting about this is that there's something here about the demographics that we need to understand about the languages and the fact that incumbent languages will continue to remain hugely incumbent regardless of anything else that happens because most of the code is written in them. And therefore, that is where most of the legacy, most of the work is. It also has this interesting effect that when I entered the business of developing software for money, as in professionally, as opposed to messing about on a home computer or doing a master's degree or anything like that, when I entered this, there's only one language I've been paid to write code in that was older than me. And I had that in my first job. I had it once after. But basically, every other language has been younger than me. That is not the case now. Typically, anybody entering the industry is working in a language that is older than them. That's not universal, but I'm going to say typical has statistical connotations there, okay? The point there is most people are coming in and they are working in a language that is older than them. So let's have a look at this highlighting. Here are the languages that are in any of the top 10s of the 3 surveys that I chose. That's quite interesting. As I say, big millennial bump there, but there is a certain strong weighting to the past as well. So let's go and look at what happened in the 60s. There's a lot of things that happened in the 60s. Not necessarily all of them good, but there was a... I'm going to pick on the Algol family. I'm going to pick on Algol 68, but I'm also going to talk about Algol 60. Algol 58 was the predecessor, but was never really formally implemented as a compiler. It was never finalized as specification. The 68 specification was actually truly finalized around 72, 73. But those ideas were out in the world in the late 60s. And this is quite important. We'll see, and there's a couple of names to pop up. Adrian Weingarten, his name's going to pop up again. But let's look at some basic influences of Algol 68. By the way, I've got this report. It is truly unreadable. It is truly unreadable. It is a good example of how not to create a language standard. But, it was early days. People didn't know. These days, we found different ways of making them unreadable. OK. Any of these keywords look familiar to you? Yeah. That's where it came from. This is where these came from. Prior to this, int was always integer. Bool was always Boolean. The idea of having varied precision types available to you, long, short, all of this, that's an Algol 68 idea. If you've worked in if you've worked in Bourne shell or any derivative thereof, bash, if and phi, that's where all that stuff comes from, okay? Struct and union, that's where this stuff came from. Everybody else is calling them records, okay? Stuff like that. So we've got a whole load of things just at the keyword level. Now, I'm going to use a running example through some of these slides. And it's going to be based on this. What are we looking at here? Fibonacci. What can we use it for? Recursion. Recursion. Yes, excellent. Yeah. Yes. Yeah, so because it approximates to phi, the golden ratio, successive ratios. It also, by the way, if you ever have to convert between miles and kilometers, yes, Fibonacci is your friend, okay? It's surprisingly accurate. This is what we've got. This is the basic idea of it. And then I have to ask you, as we're at the end of this conference, are you going to this year's Fibonacci conference? Because it's going to be as big as the last 2 put together. I got applause for that one, so it's clearly better. Well, that was an emotional tick to just release frustration. I don't know. OK, so here's some Algol 68. Some interesting things here. It's an expression-oriented it's an imperative language, but it's all based on expressions. Yeah, this is the bit that messes with people. It's just like, wait a minute, I thought imperative was always statements. Yeah, no, that's not true. So basically, everything implicitly returns a value, and therefore it is the value of that expression. You don't need to have crazy ternary operators because ifs are ifs. There's no 2 kinds of if or any nonsense like that. Orthogonality was kind of the watchword that in this language. Now, interestingly enough, this language did have a goto, but everything else about it is incredibly structured. Now, let's talk about the goto for a moment, because I'm sure everybody's is familiar with this classic Dijkstra paper, A Case Against the Goto Statement. Yeah, maybe not by that title. Maybe. OK, here's how it was published in 1968. I think it's that year again. Goto statement considered harmful. That was not Dijkstra's title. This was Nicholas Wirth's title. This is 1960s clickbait. OK? Dijkstra, for all of his ego, was just like, no, this is just a case against it. It's a modest letter for communications of the ACM. Dijkstra's kind of like, come on. You won't believe what happened to this code base when he used a goto. Yeah, it's all of that kind of stuff. Now, we're anticipating at this point this thing, structured programming. This is part of what was going on in the late 60s and early 70s. And this book was published in 72. A lot of people misunderstand the whole idea of structured programming as being just about goto. It wasn't. It was about applying some kind of structure and discipline to this kind of like Wild West of code, okay? The whole concept of block structure was impressively powerful. But again, it wasn't invented in the 1960s. For that, we go back to 1948, Konrad Zuse, Plan Calcul. Now, this was never implemented. You can probably see why. There were variants of it that were implemented in the 60s onwards, but they obviously used various compromises. But what is interesting here is some of the concepts that made their way in to this. So this is late 40s kind of programming. And let's, first of all, we can definitely see that people definitely had the mathematical bent of like, yeah, single letters, that's it, But let's pick on a few things. So what is this? This is actually a sorting function. So Konrad Zuse, known for his work in kind of electromechanical computing. Ordnung, so German, Ordnung, order. It's a sorting algorithm. I worked it out a few years back. I think this is a bubble sort, okay? Then we've got blocks, okay? We've got the idea of blocks and nesting. This is really interesting. We've got a while construct. Wiederholung is basically repetition, okay? It's condition-based repetition. We have if, but what's interesting is it's only a single branch if. That's very interesting. We're going to come back to that one. If you want to do else, you have to do the logical negation. And then in the midst of all this beautiful structure, we have break, but it's fin, which is French. Why? So here we have why not some German there? I don't know. Maybe it's because we got used to this point, at least in the in kind of a lot of classic movies, certainly up to the 30s. You either have the end or fin would be the way that you put it. So maybe that's the reason. We don't know. There was no rationale paper accompanying this. But here's an interesting thing. Just a couple of years later, we see stuff like this. This is put together by a fella. This is an idea for a construct in a language. This is 1951. This is Switzerland, ETH. And this is Heinz Ruthishauser. This is the for loop. The for loop happens to translate conveniently to English, but it's actually German for, not English for. That's where we get the for loop from. There is a point of invention for this, which is absolutely fascinating. While is a little easier, that kind of came in. We've seen that, and people kind of got the idea with while. And I need to check. I think it was in Algol 58, but certainly it was definitely in Algol 60. That was one of its big features. Most people in this room are used to something that looks a little bit like this. The original Algol 60 looked like this. And then Fortran, yeah, that one again. It looked like this, but it didn't look like this until 1990. Fortran did not have a while construct until the 1990 standard. What is interesting is there might be a couple of people in here who have programmed that and will say, no, Kevlin, I've programmed Fortran 77, we had a while. I have news for you. That was not Fortran 77. That was an extension because even the US military said, no, we need to have while. So it was an unofficial extension until finally sanctioned and blessed in 1990. So what did people do before that? Well, actually, if you were writing Fortran 77, this is how you did a while loop. Yeah, elegant or what? Definitely what. They had, and this is the bizarre thing, they had a structured if, but you can imagine somebody on the committee going like, yeah, that structured if is really good, but this while idea, that's never going to catch on, man. But here's the thing. It turns out that the while construct is actually older than if, else, and all its friends. So there's a curious thing going on there. And so this is how you would have to do structured programming or loops that you can understand in Fortran, classic Fortran 77. But GoTo does have a reputation. Oh yeah, all the XKCD cartoons were chosen by me. So in this one, I can restructure the program's controller or use one little GoTo instead. Yeah, screw group factors. How bad can it be? That's a good question. How bad can it be? Well, let me take you back to 2014. This is in Apple's SSL code. GoTo fail. This is known as GoTo fail. Now, there's a lot of questions about how did this come about, but the key point here is clearly there is not an awful lot of, the right error handling is not happening, and we have our answer. But I'm not going to lay this squarely at the feet of GoTo. I mean, GoTo has, if you've never dealt, if you've always thought it was overblown, you've clearly never had to deal with a code base that has had GoTos. I would happily introduce you to one, and then you will come begging to me to have it removed from every language you ever touch. Trust me. Remember I said I used to work in Fortran? Yeah, you will beg. But as I said, in this particular case, there are a lot of theories as to why this came about. We don't actually have a specific origin. It's most likely a copy and paste error, though some people think it was intentional and malicious. We don't know. But it's not unique to GoTo. Any form of discontinuous control flow, such as return, will actually have this kind of problem. And a number of people have suggested various fixes. There is, of course, the easiest fix, which is you say this shouldn't compile, because it's an unreachable statement. Now, for a lot of people in this room, that's going to be completely radical because it's only been around since, I don't know, decades ago. But the majority of people in this room are predominantly using a language that does not do this. This is Java that does this and first made the idea of control flow analysis mainstream. It's not that it didn't happen before. It's just that here we are in a mainstream imperative language, and you've got a language that does a definite return analysis and actually checks for dead code. Now, that dead code thing is not picked up by every language since, but a lot of them do. Most new languages say, you know what, those crazy people who like undefined behavior, that's Stockholm syndrome. Yeah, it's just like, whenever this has come up, people say, oh yeah, but it might break existing code. It might cause it to not compile. Good, it doesn't deserve to work. Why are we, there's a really interesting idea that you can use compiler switches. That's a different discussion, but it's a case of like, there should be, if you want to actually evolve a language, you have to say, and here's the line in the sand. You've got shitty code that's great, well done. I'm sure it has great business value. But if you want to play with us, here's what you do. You provide people with simple transformation and detection tools. It turns out that computers can do that really easily, but apparently we haven't cottoned onto this. But there's other things that are down to us. And this observation by Mike Bland, which I think is really interesting. Mike Bland, at the time he wrote this, he was working at Google. He now works at Apple. These bugs arouse my passion because I've seen and lived the benefits of unit testing. Okay? This strongly imprinted experience compels me to reflect on how unit testing approaches could prevent defects as high impact and high profile as these SSL bugs. That's true. Testing would have done that, but this is a talk on programming languages. So much as I like talking about testing, that's not what we're going to talk about. So I'll go to this book that I edited a number of years ago, 97 Things Every Programmer Should Know. There was a piece in it by Sarah Mount where she observed testing is just one of many tools that you can use to improve the quality of code. It turns out if you can't change the language, because it turns out that casually sitting there going like, we shall ban non-definite returns and areas of dead code that could be easily detected, if you're not in the position to change the language, because it turns out you don't own it, then there are other things you can do. And this is the basis of Sarah's recommendation. Take advantage of code analysis tools. So Java was around 1995. So was Oasis. And what do they have to teach us? This is what they have to teach us. If you have your warnings on, then you get this. So what we learn is not so much that necessarily that C has a go-to, not that it's a free format language that is prone to a very simple class of errors, but that simple class of errors is so well known. In fact, this kind of thing used to form, for those of you who've been based in the UK for a long time, there were adverts for PC Lint in the 1990s that would show you examples of code that were like that and say, oh, this is easily detectable. This is a solved problem. You don't actually have to change the language. You just have to have a better build system and a philosophy of your team to keep the build clean. Of course, you can also treat errors as warnings, and that solves the problem. So we learn a lot, not so much about the language, but about how people are not taking on the knowledge that is already there. In other words, it turns out we can solve most of these problems through existing practices or things that are known to language systems, a compiler, for example. So there are other things that we can do. Now, sometimes people use these examples and things like the dangling else to motivate. You need to put curly brackets everywhere. I used to fall for that. In fact, a lot of language designers have. I value the consistency, but it's not a logical conclusion. I've rolled back that habit because it turns out, yeah, sure, it prevents a problem, but you've still actually got something wrong there. Some languages will hit both. So, for example, Go will actually flag this. It requires the curly brackets, but it will actually still flag, hey, guess what? You can't reach this dead code detection. So the point there is that, in one sense, either you've already detected the problem or you've hidden it, and that's fine. But if it was a copy and paste error, then yeah, you haven't necessarily, you've only flipped the problem by half, which is not bad. But there is a wisdom here that we're actually avoiding talking about. The wisdom of Morpheus, stop trying to hit me and hit me. If you want this to not compile, it turns out there is a construct already in the language that a lot of people I've noticed have forgotten. It's called else. I'm going to reintroduce you to that because I've seen some really dodgy coding standards over the last 10 years that tell you to not use else after jumps. There are so many good reasons to treat that advice as poorly thought out and by people who like assembler. But one of the simplest ones is, if you use else, your code will always be more reliable. For the simple reason, shit like this won't even compile. The solution was there and was there since the early 60s, which is interesting because that does raise a question. When did we have else? Because it's an interesting, so here's a lovely talk on this by Erica Fisher. I'm here to talk about what seems like an absurd idea. If then else had to be invented. Because it wasn't part of the mathematical language, as we can see that Konrad Zusser's notation was very strongly mathematical. If you look back at mathematical books of that era, there's no else. There's another interesting thing. Else, that's not how we talk about this stuff in English. We don't talk like that. We don't say if something else, we say if something or else, or if something otherwise. So else, although itself is an English word, it does not follow English usage. English usage is to say otherwise or else. So it was not invented by a native English speaker. That one we can actually deduce. So here we've got, this is kind of leading up, this is about Algol 58 era, proposal for a universal language. Remember this bid in the 1950s and 1960s, everybody was after, we're going to have one language, just like we have one mathematical notation, unless you've actually done any maths and then you realize that everybody is fighting everybody else over particular notations. It's just there's only one notation set taught in school. So here we have, we've got a mix of Swiss and German contributors. There's Heinz Rütishauser, inventor of the four. Klaus Samuelson, watch him, German physicist, if I recall correctly. And so we've got these names. And they're, interesting enough, there is an else in this spec, just as there is a letter lambda, interestingly, but it's not the lambdas. We'll talk about them later. It's not the lambdas you're thinking of. That else was simply used as a description for dealing with three-way comparison. It was a documentation thing. In the preliminary report, Alan Perlis was the first recipient of the Turing Award, given that we're picking out Turing Award winners. And there's our friend Klaus Samuelson. This is what it looked like. Blah, blah, blah. Here's the operators. Go to, do, return, stop, for, if either or if. There were two forms. There was one for a two-way comparison and one for a multi-way. But by the time we got to Algol 60, Klaus Samuelson, inspired by the work of, here's a few names. We've got Bacchus, we've got Bauer there, Perlis, Rütishauser, there's Adrian van Wijngaarden, some fairly key names. But John McCarthy, inventor of Lisp, he'd been messing around with conditionals. He had some ideas. And Klaus Samuelson said, I've got an idea. That's where else was born. It arrived in 1960 along with while, but had actually been, else had just been invented just slightly before that. So we could go into language constructs forever. And I was really tempted after Khalil's talk the other day to say, you know what, let's talk about the history of exception handling. And then I realized I did not have a day and a half. I only had an hour and a half. So we will skip that one. I will make a couple of comments about that as we go through. But the next, when we start talking about blocks and blocks of control, we have things we call functions, procedures, subroutines, they're variously called different things in different languages. And really, honestly, these days, the only people that use the term subroutine are programmers of VB, Fortran, and Star Trek. Yeah, you'll see that they still, in the 23rd century, they've gone back to calling them subroutines. But that's because that franchise crystallizes the language of the 1960s. Okay, so they are using that. As an aside, don't let mathematicians say you're misusing the word functions. The word function means exactly what you think it means, and then there is a concept of a mathematical function. That's a specific type. They don't get to own that word. This one was around for a lot longer. Okay, I'm just going to point of clarification there. So here's an observation from Donald Knuth. Subroutines are special cases of more general program components called coroutines. In contrast to the unsymmetric relationship between a main routine and a subroutine, there is complete symmetry between coroutines which call on each other. And here's a thought. What he's saying is this is a general approach. And actually, there was a lot of discussion about this up until about the end of the 80s. And around the end of the 80s, this whole idea of coroutines started going away. And cooperative multitasking was pretty much gone as a kind of default way of doing stuff on certain classes of system by the mid-90s. Only Apple were kind of clinging onto it dearly for a few things and then decided to reintroduce it with iOS. Every time somebody does that, they eventually end up with a preemptive system. But what was interesting is coroutines disappeared off the map as a language construct. And Knuth highlights the fact that the person that invented them was Melvin Conway. And if you're familiar with Conway's law, yeah, it's the same Conway. Melvin Conway invented coroutines in 1958. Here is an early 60s paper where he talks about how this can help you write a compiler. The reason I highlight this important point about history is that coroutines are actually older than, that means the else and while statements. They are one of the oldest sequential and procedural constructs that we have available to us. I say that because a lot of languages have been getting in on the act recently, and I've even seen blogs where someone said, there's this new idea. It's 1950s fresh, okay? Coroutines are subroutines all at the same level, each acting as if it were a master program, when in fact there is no master program. The coroutine notion can greatly simplify the conception of a program when its modules do not communicate with each other synchronously. This idea was prevalent and was in people's heads. So Clue, very influential language, was actually used as a teaching language up until the 1980s at MIT. Barbara Liskov, if you've come across Liskov substitution principle, yep, that's her. And she won the Turing Award in 2008. So these are fairly high-profile individuals. Now, what is interesting here is that in Clue, we find a language with a lot of the concepts that are familiar to us. We have the terminating, the block-structured termination model of exceptions that we are familiar with now. This is where it comes from. Okay, it's this language. There's a bunch of stuff here. The idea of having iterators. Her observation is that iterators are a form of coroutine, not the iterators that are separated out into separate entities that we find in C++, but a routine that runs in parallel, effectively, with the thing that wants something from a loop. So they are effectively concurrent. And so they were present in the language. Okay, she introduced them in that, her and her grad students, that's the folks on the rest of the folks on the list. However, their use is sufficiently constrained, they are just implemented using the program stack. That's an important observation because their use doesn't require, a coroutine requires a separate stack, but she recognized, yeah, effectively, these run concurrently, but in practice, their use is so constrained we can get away with it. And so here is some Clue, and there's some really nice things in here to note. Just for those of you who care about language history, well, you must do. You're in here. So we've got the yield keyword. Okay, it's 1973, 1974 we're looking at here, just to give you a sense of how new this idea is. We've got multiple assignment. We've got optional commas. Optional semicolons. I didn't learn about that until relatively recently, actually, because all the early papers include semicolons. It turns out you didn't need them. So there's a whole load of stuff here. You've got declare anywhere. That's actually Algol 68, that's not Clue. But there's something here that's really quite interesting. If you program in Python, then yeah, all of these features are there. In C#, this is an interesting thing for me with C#, because when C# introduced iterator methods, I remember, so this was around 2005, C# 2, if I remember correctly. I remember thinking, oh, they've introduced yield keyword and they've introduced these. I said, oh, that's at least a foot in the door of coroutines. I wonder if they're going to go all the way. The answer to that question was no. Disappointingly not. They made the same observation that Barbara Liskov did. It's just like, sufficiently constrained, we can kind of get away with using the regular stack and a couple of continuation points. And then we have C++ here, where we have to do a little bit more faking to get some of the effects, but no, it still kind of works. And of course, you can only do that officially since a couple of years ago. The std generator, I mean, the way that C++ came along, C++'s history is, hey, we're going to introduce a thing in the language, and nobody anywhere in the library is going to use it. That's a philosophy of the C++ standard. I know there are some standards people in this room. I am mocking you. We're going to introduce a feature, and we're not going to use it. That's how good it is. What? No, we're going to wait and see how no, that doesn't work. Nobody else does that. Look at every other language. So until 2023, you couldn't really do anything useful and convenient. You could do useful things, which were pet projects and do lots of talks about them. They're really good for talks because nobody understands them, because basically it's the IKEA approach without the instructions. But fortunately, we can just put that on the end now, and it's just as easy as it was in other languages. But here's an important idea. For all of my mockery, there's the whole point here. This is really important because C++ is actually reclaiming part of its origin story. Part of its origin story is way back in the day. As Biana recounts in Design Evolution, which is a truly wonderful book. I wish more people involved in language design would write these things because it really gives a very deep rationale. But he said the first real code to be written in C with classes, as was called then, was the task library. So task.h was available on a number of platforms till the end of the 1980s. And it was really only in the 1990s it started disappearing or becoming non-standard. It was never standardized. And Biana's background, Biana had learnt Simula, the kind of original object-oriented language, Simula 67, and had worked and had learnt Algol and then learnt C. And when you realize that, you start realizing an awful lot about the influences on the language. But this was really an important one. As far as he was concerned, this was kind of the reason he needed this kind of simple concurrency model. But what is interesting is this actually predates the concept of objects. People often talk about Simula 67. In 1965, the first version of Simula, excitingly called Simula 1, actually did not have what we consider to be objects. It had the process model, which was a coroutine model. Simula 1, a process was a bunch of data attributes associated with a single action known as the process's operating rule. Each process's operating rule could be suspended or resumed at any time. Basically, they were a coroutine. In fact, most reports are not as hesitant as this one. They were a form of coroutine. So this is kind of an interesting so in other words, C++ has reclaimed territory that it had at the beginning of its life and then kind of lost out for most of its history. So let's go back to one of these things. And this is something, there's a couple of things here I've touched on in other talks that I've done at ACCU, but I do want to recap this because having just mentioned structured programming and stuff, and the importance of block structure, one of the most powerful mechanisms for program structuring is the block and procedure concept. That really, for me, is one of the most important innovations. But what is interesting is that it is considered to be deeply powerful. So hopefully everybody's reasonably well fed and is not salivating at this pancake stack, which is a stack. So here it is in an Algol 60-based language. Truly block structured in the sense I'm able to put procedures inside of a block. And wherever you declare a block, you can declare state, so variables. There you go, integer, not int. This is Algol 60. By the time they got to 68, they decided to knock off a few letters. These are not source code compatible, these two languages. We've got a count. References were an extension. We've got arrays. It's called array, imaginatively enough. And you can introduce your own procedures. So in other words, a block can have state and it can have action. It can have procedure action and operation there as well. Now, here's the interesting thing, is the observation that was made. Uli Johan Dahl was one of the developers of, it was him and Christian Nygaard, developers of Simula 67. As far as they were concerned, remember I said structured programming was not really just about the go-to. It was about structuring, systems of structuring. And one of the things they had in the section of the book called hierarchical program structures was this crazy wild idea called classes and objects. In other words, object orientation used to be part of structured programming. It's just that you couldn't do much with it. If you were in Fortran, honestly, as much as you could do was, we'll use if and else, and then we'll use goto to fake up whiles, and the rest of the book was irrelevant because you just couldn't do it. But the observation here is a procedure which is capable of giving rise to block instances. Remember, blocks contain state and behavior, and they disappear, according to stack discipline, at the closing curly or the end. Well, what if they didn't? What if they stuck around? And you could say, here's a bunch of stuff, and you can do things with it, and it knows stuff, and I can pass it to you. Boom, new paradigm. So really, blocks were the origin of all of this stuff. Procedure which is capable of giving rise to block instances which survive its call will be known as a class. The instances will be known as objects of that class. And that was what you did. You put class in front of the block. That was it. So the block, every time you use that and you go new, it just like creates a thing. Awesome. What is interesting, and a lot of people don't know, is that that data is automatically public. And so although people often look to Simula as like, hey, this is, original object-oriented language, it wasn't until 86 they put the hidden keyword in. And as they didn't choose private or anything like that, but by this point, the cat was already out of the bag, and there were other ideas about object orientation, and the notion of privacy was a very strong one. And so hence why Bjarne did not choose words like hidden, which existed in some extensions, chose the more natural ones. Why? Well, this is public. What should we call it? I don't know, public sounds like a good way of describing something that's public, and the opposite is private. So, you have that. The one in between was a bit tricky, and protected doesn't really do it justice, and I'm not sure there is any word that can do it justice. So, naming is hard. That's all we know. But this is data abstraction. This was not a new idea. So there's a really interesting thing here. There is a separation in the history of how many people think about objects. We normally think of encapsulation as being to do with privacy, but actually originally the term just meant putting together. It's a capsule. It just doesn't necessarily have protection. But that was not a new idea. It's Barbara Liskov again. Barbara Liskov did something rather neat in 1974. She invented, 1973 and 1974, she invented the abstract data type. An abstract data type defines a class of abstract objects which is completely characterized by the operations available on those objects. This might sound familiar. A programmer is concerned only with behavior that object exhibits, but not with any details of how that behavior is achieved by means of implementation. Now, what is interesting here is that when she received the Turing Award in 2008, her husband made an observation. He dug around, went online. Internet was just in case you're wondering. The internet was still pretty toxic by 2008. 2008, the internet was toxic. Wasn't quite as toxic as it is now. Back in 2008, we didn't think it could get any more toxic. We were wrong. Just for the record. But what was interesting is he went online to find out what people were saying, and there were people going like, Barbara Liskov's been given the Turing Award. Yeah, but everybody knows this stuff. Yeah, because Barbara Liskov invented it. It's now when she went back to MIT to do a languages course, she spent all her time doing distributed systems and stuff through the rest of the 70s, 80s, and so on. She went back, and she's suddenly like, I don't have to teach this stuff anymore because it's already part of, the first year syllabus and stuff like that. The point is, it's become... there's a certain erasure going on here, but yeah, she was kind of responsible for, no, this is serious stuff. We should not merely put stuff together. It's, avoid access. And that idea was taken up by a number of people. Nicholas Wirth in Modular 2. The Ada language. Isaiah did, it was the whole idea of like, we should formalize this in the language. And here is the first abstract data type stack. I think I mentioned this in a talk here a couple of years ago, but I'm going to mention it again because we're at this point that this is the first one. So push, pop, top. Just for the so there's a lot of stuff here that is fairly easy to pass, but for anybody working in languages where they don't use top, they use crazy stuff like peak. No, top is the correct term. You don't peak at something. That doesn't make any sense. This is, Barbara says so, and I'm with her. But this is the first abstract data type stack. And she was inspired by Parnas's paper, which is 1972. Criteria to be used in decomposing systems into modules. A data structure, its internal linkings, accessing procedures, and modifying procedures are part of a single module. But this is not the only way to organize this stuff and hide things away. There's other approaches as well. Again, 1970s, this is 1978, 79, can't remember exactly, but it's kind of like, I think we're heading into post-punk, new wave. Certainly Blondie were in the charts by the time this came out. The question is whether or not the Sex Pistols were still in the charts. I don't know, I'll have to check that. So there's a whole load of stuff. You will also see there's a couple of references. There's Clue and even PL1. But the key thing here is processes. Processes as a unit of abstraction, if we can make that first class. And what's most interesting about this paper is it introduced this idea of channels as a way of communicating between sequential processes, rather than thinking of three-threading and low-level concepts like locks. The idea is, the thinking was in academia, it's like, yeah, locks are obviously a bad idea. We should never put those in languages and libraries. I'm just going to say that again, just for the record. This was a known thing, but it's just like, yeah, this is obviously how you're supposed to do it, channels. And this was the first language, Occam. Well, in fact, second language is Occam 2, but I originally read the Occam spec, but then eventually ended up doing a master's degree where we were working in Occam 2. Occam 2 is very weak data abstraction. Its successor was supposed to have an awful lot more, but it never kind of happened. But Occam 2 had some really interesting ideas, which are, let's have a look at them. Here's Fibonacci. The ideas are proc. It can be either a procedure or a process. If you run a proc and you wait for it, then it is a procedure. If you run a proc separately in parallel, then it is a process. Yeah, cunning use of the spelling there. There is a channel of int. It follows kind of algol type prefixing. So just to clarify, that is where you put the type first. In fact, I say algol, but it was actually Fortran. You put the type first, here's an int, and then there's the name. That idea was seen to be okay. It was a 1950s idea. And it was seen to be okay because the set of type names was fixed, and you never had long type names. The Pascal people had it right. That ordering is disastrous for anything involving the opportunity to create your own data types. But one thing in Occam was you just couldn't create your own data types, so problem solved. And then you had the idea of a sequential block. And this was, there was a counterpart idea, a parallel block. In other words, you could take a bunch of statements and just say, no, these are all in parallel. It was beautifully orthogonal, strong nods to Algol 68, which also, by the way, had a par keyword for parallelism, but lacked channels. And we have the ability to send things out. So we can communicate, you can sit there, you can run Fibonacci in parallel with yourself, and you can just kind of, you can receive from it, and it will give you the successive numbers. And also Occam, so this is a 1980s language, also had multiple assignment, and it also relied on indentation. So this was not a Python idea, this was not a new idea when Python adopted it. It was already old. It had been used in a couple of languages, but for my money, most notably Occam from around, I think about 83, I think was when it first kind of came onto the scene. If we do this in Go, the language that most people associate with channels and things like that, Go came along 2 decades later, basically. And channels are a good idea, just generally as a way of thinking about the relationship between, hey, you're a thing running in parallel. Maybe we should share some data sometime. No, don't do that. Maybe we should share some data and come up with a complex arrangement of locks. No, maybe we should just have a channel. And the thing about Occam that I always find absolutely fascinating from a point of view of language design, it is the most strictly typed language I have ever used. Nothing else comes close. Ada is an absolute lightweight. It's practically JavaScript in comparison. The compiler is also, I mean, people often talk about opinionated languages. Oh, you have not met the Occam compiler. You know those times where you're doing a big build and, oh, you forgot something, and then boom, there's this cascade of errors. It's just like, oh my goodness, not Occam. One error. That was it. It would stop at the first one. You know, it's just like, that's it. I'm not going any further till you fix that. That was it. It would not give you this wave of errors. It was just like, that's it. And the thing is, it was so statically typed, and so everything about it basically meant that your program compiled, about the only thing that could be wrong with it was possibility of deadlock. So, but it also had a bunch of other ideas and little innovations, one of which is it did have the idea of functions that were pure functions. I mean, they were pure functions. If you even so much as put a hint of state change inside them, it just wouldn't compile. And there was no workarounds, there was no mutable or any kind of hacking. They just would not compile. They were true functions. Again, this one made Haskell look like JavaScript. Okay, this was brutal as a language, but one of the most consistently designed and simple languages I've ever had the pleasure of using. So we've got a bunch of stuff going on here, and we can see a lot of ideas come to us from the past. In one sense, that's not really surprising. But there are other, and there we go, multiple assignment again. So it's just a case of like, it kind of bounces through history from the 1970s. Actually, no, I traced it back. 1960s is where multiple assignment came from. For those of you familiar, what language? Okay, C++ extended C. What was C the successor to? B, yeah. Technically, there was actually another one, a little sideshow called NB, which was B with types, but that doesn't get a lot of press. B, and where did B come from? BCPL. And what's the B in BCPL stand for? Well, more to the point, what's the CPL stand for? Combined, very close, guy. Yeah, Combined Programming Language. It's a joint project between University of London and University of Cambridge. Guess what? It was another language that's going to be the final language. Yeah, one of those. Combined Programming Language. Combined because it was two universities, yeah? But it was a little more complex, and so a couple of people, Martin Richards, Colin Whitby-Strevens, walked away and said, well, let's have a basic version of this. That's word-oriented, BCPL, basic CPL. BCPL is where / comments come from, and a couple of other ideas. And there, you can actually tell that the designers of Occam who had also used BCPL in terms of the way they had structured functions. But what is also interesting is that CPL had multiple assignment, or parallel assignment as it was called, but BCPL did not. But that's the earliest I've been able to find it. If anybody can find anything earlier, that'd be great. But it's around the mid-1960s, somebody had the idea of like, hey, A comma B equals C comma D might be a cool notation. It makes swaps a lot easier. So what we are looking at here is a rather interesting case is that, of course, we know that. Other people have ideas, and sometimes it takes a long time for them to get into the mainstream. But Backus was impatient because as far as he's concerned, this is 20 years, this is still a young profession. How is it that we are still stuck where we are? Conventional programming languages are basically high-level complex versions of the von Neumann computer. The von Neumann computer idea from John von Neumann is basically we have, here is memory, and here is the thing that kind of processes memory, and we have this kind of bottleneck of instructions come from memory, and then they need to be processed, and we go and get stuff from memory. It's a very elegant and simple separation of concerns, but there are certain scaling issues. And he basically said, look, von Neumann programming languages, as he termed them, use variables to imitate the computer storage cells, control statements elaborate its jump and test instructions, and assignment statements imitate its fetching, storing, and arithmetic. And he was much more interested in a very pure version of functional programming. The idea that we focus on data flow and data availability and a whole load of a different way of thinking. So let's go back to those 30 languages, all of which made some top 20 or other in our list. And let's look at all the languages that are functional programming languages. There we go. Right, so we have an answer to John von Neumann's, John Backus's question. Now, that does not mean that the ideas of functional programming have not had an influence. Here are all the languages that have features that have been directly or indirectly influenced, or by their users. Sometimes people say, I am using this, therefore I am doing functional programming and I'm adopting a functional idiom. Yeah, I'm not going to debate that. That's an interesting discussion in itself. But these are all the languages where we can make that claim reasonably. Not a single one of them qualifies as being declarative. The only one that actually qualifies as being declarative is SQL, and that's not functional. It's actually what's called a logic programming language. But what is interesting is that many people in the functional space try and kind of a little bit of overreach, try and say, oh, that feature, that's a functional feature. No, it's not. It's a declarative feature. Just for clarification, declarative languages form a very large category, and then you have imperative languages that form a large category. And then within declarative, there is functional, of which functional is the best known, but it's not the only player. But all declarative languages have this idea of like, yeah, we don't really have side effects, and you know, it has a mathematical purity to it, but it just looks a little different to function composition. And SQL is mostly based on set theory. This is what COD was looking at. So we end up with stuff like this: so number from number, where number is divisible by 2. If we want to do that in terms of a list comprehension in Python, then we can see the form is very, very similar. If you're doing this in Haskell, again, the form is very, very similar. That form we refer to as a list comprehension, and it is a syntactic construct. It is a sugaring, but it's a very simple one, nice and easy to work with. We tend to think of it in terms of list, but it comes from the mathematical notion of a set builder or set comprehension. If I were to write that in set form, mathematically, it would look something like this. Number, where number comes from the set of numbers, mod 2 is 0. So we have exactly the select from where structure. Now that also informed this in C#. Now what is interesting, this is link in C#. What is interesting is that C# kind of broke away in the early 2000s, broke away from a very long tradition in programming language design. The tradition of keywords being completely and utterly reserved. This is an interesting idea because back with Fortran, there wasn't an idea that there were words that were special. It was about where they were in the syntax. So you could have an if statement that was if equals then equals end if. They were not reserved and treated as special. And this idea, people wrestled with the idea of specialness for a while. And it is also why if you look at there's a little bit that I kind of glossed over, but let's go back to it. Let's look at the Algol 68 that I showed earlier. The keywords there are in bold. This was left as a somewhat open feature. It's not the Algol 68 standard. In fact, any standard at that time for languages was not as crisply and fully defined as we have come to recognize language standards. That bold is basically somehow is an indicator to, if you're writing the compiler, somehow make this special. So I've done it through the power of font emphasis. And that was actually how it always appeared in books. A typical technique, and this was known as stropping, you could choose, and there was a compiler switch, was to say, you know what, everything's going to be lowercase except keywords, which should be uppercase and be in the uppercase space. Or you can put your keywords in quotes. There are lots of different techniques, but it was basically, there is a separate world where these keywords exist, and they will not interfere with this. You just had to define what that world was. Well, clearly, that's not really going to work very well. And languages like Pascal and C basically said, no, if this has got to have any portability at all, this is it. The thing that you see is the thing that it is. There's no kind of clever workarounds. And that kind of helped inspire this idea of reserved keywords. But as languages have grown, the one thing we've discovered is that if you keep adding keywords and you start moving and you have pre-existing code bases, you are likely to start choosing words that other people have used perfectly innocently for variables. And so therefore you end up with contextual or special. There's lots of words people kind of work around, you know. And this happened, I remember seeing this in C#, going, wait a minute, what if I've got a variable called from or where? It doesn't matter. In this construct, they're special. So in this construct, I cannot have a variable called from or another variable called where. But I could have elsewhere in my code as long as it's not a link statement. But we've also now seen this has now jumped into pretty much every other language. It's kind of like, oh, this is a good way around it. Yeah, you got that C++ code, you can have an override keyword there. I say it's not a keyword, I can make it a variable as long as it's in the right place. Even Python has now started going around saying, yeah, we've got special keywords depending on their context. It's kind of an inevitability of growth. It turns out that at one level, the keyword idea is a really good one for a fixed language that does not evolve. And it's just like, actually, it gets a bit awkward after a while. Either way, yeah, a lot of .NETers won't write this kind of code. They'll just write what the underlying thing is. Rather than go for the syntactic sugar, they will just write, yeah, this is what it compiles down to. If you're doing this in Java, they don't bother with syntactic sugar, and they say, yeah, well, this is how you do it. And of course, if you do this in C++, then you run out of space. Yeah, using namespace and a little bit of formatting can help us there, but there is an interesting note about how these things are or not as brief as they could be. And that also highlights another trend, that there is a brevity to these. Now, there's two things that I want to note here. One of them is to do with lambdas, and the other is to do with pipelines. The pipeline idea itself is very old. And I've talked about that one here before. The idea of this being a very simple and elegant way of composing things, even if you don't have true concurrency, is a great way of thinking about it. The idea of this pipeline actually dates back. This is Doug McElroy. This is Doug McElroy's memo in 1964, and this is Brian Kernighan's copy of it. We should have some ways of coupling programs like garden hoses, screw in another segment when it becomes necessary to massage data in another way. This is the way of I/O also. So he invented the idea of the pipe, but he did not cut in, and the metaphor, but he did not invent the symbol. That was Ken Thompson. In 1970, he said, I'm just going to use that symbol. Because everybody was arguing about what's the best symbol, and he just sat down one morning and said, I'm choosing it, whatever. Very hands-on. But the other thing is this other functional notion, the lambdas. So Simon Peyton-Jones, who gave a talk here, the choice of font, does anybody know where Simon Peyton-Jones works? Microsoft Research, yeah. Thank you, Microsoft, for giving us Comic Sans and great color schemes. So made this observation, and it's made it in a couple of places. I certainly remember he did a talk at ACCU 2003, 2004, thereabouts. Excel is the world's most popular functional language. Okay, because it actually has not all that crazy VBA stuff in it. That's definitely, blatantly and brutally procedural and imperative in nature. But the actual macro language and the relationship between cells is pure data flow. In that sense, it's quite elegant. Which I often joke is like pisses a lot of developers off, because it turns out the people in their accounts department have been doing functional programming for longer than they have. But there was something that Excel didn't have. It did not go the whole hog. It did not have lambdas. And I actually made this observation. Don't put lambdas in there. It's not going to help. When did I make this observation? I made this observation in March 2020. Some people may remember things were happening around March 2020. This was the last conference I did in person for a number of years. But I made a throwaway remark. But here's the thing. 2020 gave people a lot of time at home. And they got working on their pet projects. And they did, and for a lot of people that was very exciting. For others, very depressing. Oh, there's lots of things going on there. But I know what they were doing at Microsoft, because in December, they announced, we're going to put lambdas in. And I'm just sitting there going like, oh my goodness, Excel spreadsheets are known to be mostly buggy. The idea of giving these people, lovely, lovely people, lambdas does not sit well with me. Anyway, you can now do lambdas in that, and you can now do them in Google spreadsheets as well as a result. So, you can do Python in, I'm a little happy with that decision. But the idea of this is quite fun, but it's really not something you want to let most people get anywhere near, unless you're doing a talk and want to show this is how you do church numerals in Excel. So there's the point. This all comes from Church. Unsolvable problem of elementary number theory is 1936, and and what a lot of people think of as the genesis of lambda calculus, but actually it came from a previous paper in 1932, set of postulates for foundation of logic. So lambdas are quite old as an idea. And what was also interesting is the late William Cook made an observation when he was revisiting a paper on data abstraction from the 1980s and talking about object orientation. He said, actually, we can demonstrate that lambda calculus was the first object-oriented language when he looked at concepts of closure. It's very interesting observations he makes there. So I'm going to borrow from XKCD. If you've not seen this one before, this is, well done, today's your day. Fields arranged by purity. Sociologists, psychologists go, sociology is just applied psychology, psychology is just applied biology, biology is just applied chemistry, physicists, nice to be on top. And then you've got the mathematicians all the way over here going, oh, hey, I didn't notice you guys all the way over there. So, I had the good fortune to go see Randall Munroe last year on when he was on tour. The second time I've seen him. He's definitely, if you ever get the chance, do see him. I'll just leave you with one quote here before we get back into the lambda stuff. He described himself as not patient enough to be an engineer, but too anchored in the real world to be a mathematician. And that's how he ended up doing XKCD. But let's do this. Languages arranged by when they included lambdas. So Java was really late, 2014. C++ got in there before Java. C# had it in the 2000s. Then you have JavaScript, mid-90s. You had a very simple idea of the lambda there. And then Smalltalk 80, which was like, yeah, that's pretty cool. And then, Lisp. I'm listing Lisp as a 1960 language. Sometimes people list it as a 1950s language. It existed in paper form in the 1950s, and I'm not giving credit for papers. The first implementation existed in 1960, okay? And this was John McCarthy and colleagues. And there's a number of things that are interesting about the original language. It's very elegant, took a very different path to things. The original form of doing a conditional looks somewhat like this, defined a function, Fibonacci, takes n, and then you had a conditional construct that we actually see kind of echoed in, suggesting the conditional construct kind of, we see it in languages like Erlang and in Occam and things like that. The idea of like, we'll just list off a bunch of conditions and consequences, and then we'll match the first one. And the last one we list as true, and then we do that. Later versions of Lisp actually formalized the kind of the more then-else form and the idea that you have to, but this is kind of the classic original form. And this was kind of inspired Klaus Samuelson and others in their thing. But here's the interesting thing. Let's talk about Lisp for a moment. What is the domain that Lisp is best known for? Where did it come from? AI. Yeah, that was, it was originally associated. So Lisp was the staple of the symbolic AI era. And in fact, Lisp came to define a whole family of things. In fact, that used to be kind of a standard joke. If you were an AI researcher, the first thing you'd do is design a new Lisp, And some of those have escaped into the wild, Scheme being the most famous. But most of them is just like, oh yeah. And when you look through, a lot of these things have very evocative names, planner, mapper, stuff like that. But when you look through, you go like, oh, it's another kind of extended Lisp or another reinvention of Lisp. So this takes us to the question of machine learning. A machine learning algorithm walks into a bar. Bartender asks, what do you have? Algorithm says, what's everyone else having? And that's kind of an interesting point because that is what you're very much looking at. And so there is this question, this has been a point of discussion amongst a number of developers and certainly this conference last week. And there is this question, can language models replace compilers? It's one of those questions that keeps popping up. So we've got the idea of I can use LLMs conversationally. I find that very useful. But you also have to know what, you almost have to half know the answer. Yeah, as somebody posted and said, it's really funny. Whenever I talk to ChatGPT about stuff I know, it's wrong on so many things. But whenever I ask it a question about something I don't know, it always seems to be right. You kind of have to know. But that's the point. It's a conversation. There's a dialogue going on. And people talk about it using for generated code, and there's a remarkable amount of generated code out there now that people have completely ignored all the advice on, as in, yeah, be doubtful about it, be skeptical, run it against tests, crazy ideas like that. And there's a lot of that code out there. But the question has come up, what if we just version control the prompts and then just, vibe the rest of the way? Don't get your hopes up. And there are a number of reasons why this is not going to change. Or you should certainly, if you are generating stuff and significant amount of stuff, do hold on to your prompts for a variety of reasons. But this comes from Mike Lakides. Now, Mike works at O'Reilly. Mike and I have been having conversations that started back in 2020, given that I refer to the pandemic. Mike and I just, we started having conversations every 2 weeks. And we are still doing it 5 years later. Every 2 or 3 weeks, we get online and we just have a chat about each other's families, what's going on in the world. And obviously IT comes up, also AI stuff comes up quite a lot. And back in 2021, we were talking about, well, what about thinking about it as some kind of, well, I don't think we used the term copilot. Kind of wish we did, because that would have been a wonderful historical record. But we did talk about it as pairing and all this kind of stuff. Yeah. But we've also explored a number of other things. My thesis to him is what happens when most of the code generated becomes the basis for further training. I didn't know the terms model collapse then, but we kind of talked about that then. But one of the ones we've discussed has been about this. Kevlin Henney and I recently discussed whether automated code generation using some future version of GitHub Autopilot or the like could ever replace higher-level languages. Kevlin made the point that higher-level languages are a repository of determinism that we can't do without, at least not yet. Now, this is really important because this idea of a repository of determinism is, I don't want the flaky, wishy-washy English of emails. I don't even want the precise English that some of us are actually quite good at. What you want is that thing that we wrote produces something that is functionally equivalent every single time, without deviation. When you talk to compilerize, the idea of just like, when we talk about backward compatibility, the idea that your whole business is going to depend on something that could be that you can't version control. You can version control the prompt, but you don't control the other end. But there is this point, and you can turn the temperature all the way down on this stuff. You have no control over it. The idea that you could end up your whole business crashing just because of a small shift in semantics, and trust me, English has a tsunami of shifts in semantics often enough. And we are very careful to guard those and to be able to use that language very precisely. That's why we have notations that are precisely defined. That is their value. It's not to be weird and quirky, although every single programming language is weird and quirky in one way or another. The point here, the process is not repeatable. If you gave me a system that is not repeatable, I do not want to base my language on it. If you talk to product managers of compilers and language designers, they do not want flaky, wishy-washy kind of, yeah, we just changed this. We'll change the meaning of this in the next release. Here is a keyword everybody's relying on. We'll change its meaning. We can't, let's go back to something earlier on. It's so conservative in that sense that we can't even change the C and C++ languages to be safe easily by saying that code is shit and has no right to compile. Oh yeah, it's only a small percentage, although I think actually, having looked at some of the stuff out there, yeah. But, we can't even do that. Can't even fix a problem when it's known. Imagine if you don't even have awareness that you're trying to fix or something is being done. That's the problem here. So an updated model is likely to produce completely different source code. The natural language prompt can't be the repository of determinism. So please do version control it, but what you're getting out of it is not guaranteed to be the same each time because it will be improved in some way next time, which is great for certain things, but you really need to have control over it. So what we're left with is an observation that I made gratifyingly a long time ago. The act of describing a program in unambiguous detail and the act of programming are one and the same. You still need to do the stuff. We still need a programming notation. We still need languages. That is a really important idea. What is interesting is what some of the advice that you get for working with LLMs, if you want them to do stuff, is like, oh, well, okay, I'm going to create a special language. I'm going to tell the LLM, here is my language. This is what these words mean. And from this point on, we will do this. This fits with Feynman's observation. We could, of course, use any notation we want. Do not laugh at notations, invent them. They are powerful. In fact, mathematics is to a large extent invention of better notations. I would say the same is true of programming languages. But there is an issue here that we have in the mainstream. It's not that people aren't creating a lot of languages. Let's go back to John Backus. He made this observation in the late 70s. Each successive language incorporates, with a little cleaning up, all the features of its predecessors, plus a few more. Now, at that point, he could not have known what we know about how languages evolve. Each succession, what we now know is that each successive version incorporates, with a little cleaning up, all the features of its peers, plus a few more. What you are finding is that programming languages, I'm not saying they're all becoming the same, they're not, but they are all drawing from the same set of features. I can literally pick up a new language and say, how do you do lambdas in this language? And there's a very good chance that somebody will go like this rather than we don't have lambdas or what's a lambda, okay? How do you do loops in this? Even if it's, I can even do that in a lot of functional programming languages, and even though it's not idiomatic, it's just like, it's probably got a way of doing it. The point is that the question has meaning in that context. And so what you've got is that we've ended up with programming languages, and this is quite important from the point of view of when we think about the future and the impact of LLMs. Programming language evolution for the mainstream is slowing down. And I kind of notice that when I think about the examples and kinds of languages that we have available to us. People are still inventing lots of languages. It's just whether or not those gain traction. The answer to that is generally no, they won't. They will gain less traction than they would have done in the equivalent period in the past. For the simple reason, and another conversation between Mike and I, an observation we kind of had a few years ago is like, people have kind of stopped talking as much as they were about functional programming ever since they got the functional features they wanted in their languages. It's like, I've got a choice here. I can either try and program in Haskell, or I can get some of those features into my language. And that means that we get to preserve the code base. I get to preserve a good place on my CV, and all the rest of it. And what's interesting is that interest in Haskell has actually waned in the last few years. It kind of went up, and then it's just dropped again. Now, that's not to say that all these languages that have been adopting various features are comparable. Remember, this is not a quality judgment. This is a quantity judgment. But many of the things that people wanted, they are now sufficiently satisfied with. They could be more satisfied, but the point is they're getting those features in their language. And so therefore they get to keep the same language. They're keeping the same language and it's getting features. So we have that. What is interesting is that what you're looking at in the bulk of languages, the bulk of the mainstream languages, is that those language names I showed you earlier on, they're going to be with us for a long time. They're just going to, what each language means will change with time. But also we should be very aware that even adoption of new features is not necessarily going to help, because LLMs are biased towards the past. That's where their training data comes from. So if I create a new language today, there is no LLM support for it whatsoever. Okay? If I choose a language like Python or C, Java, the amount of stuff out there is huge and is way, way huge. And importantly, most of that stuff is old stuff. That's why we call legacy systems. And legacy, that is our inheritance, so to speak. I didn't touch that in this talk, but there we go. That is the inheritance that basically in future, and this actually relates to Jason's concerns about in terms of style. If you're starting to ask for C++ to be generated, there's a very strong chance it will be historical C++. And we've also seen, I read a JavaScript blog the other week about its bias towards certain frameworks, because that's where most of the blogs and the commits and the noise is. And what happens is you're ending up with a multiplier effect on things that are already dominant. They have their own multiplier effect, but that becomes an effect in itself. So let us return to this, and I need to make one observation. There is a question in the title. Can programming be liberated from the von Neumann style? Has anybody come across Betteridge's law? The maxim that any headline that ends in a question mark can be answered no. That is the answer to John Backus's question. Now, That's just simply the observation. As Faulkner said, the past is never dead. It's not even past. Now, this, I want you to understand, I'm not sitting here with delight at this. I'm actually a little bit depressed because there's a bit of me that, in fact, most of me is an optimist. And there's another bit that sort of says, yeah, innovation. And what I'm seeing is not that. And in fact, all the evidence is pointing the other way. That is slowing down. Does not mean that people aren't innovating. It just means that, well, the bulk, what's happening in the bulk is actually surprisingly predictable and surprisingly slow moving. And that we've kind of seen, until something major happens, until something radical happens, this is the story of programming languages for the next few years. Thank you very much.